Extruders are common devices in the plastic, metal, and food processing industries, and the utilization of extrusion processes is particularly widespread in product manufacturing that uses polymers as a raw material. Typical products made from extruded polymers include, for example, pipes, hoses, insulated wires, cables, sheets and films, and tiles. Generally, major extruders are classified as a single-screw or twin-screw type, the former being widely applied to general polymer processing and the latter for compounding various fibers, fillers, and polymer blends before final molding. Twin-screw extruders can be further divided into two types based on the interactions of the two screws: intermeshing and non-intermeshing twin-screw extruders. In the twin-screw extruder family, fully intermeshing counter-rotating twin-screw extruders have been found to have the best pumping abilities because of their positive displacement characteristics. Intermeshing counter-rotating twin-screw extruders were developed from continuous kneaders in 1939 as part of the modules intended for compounding, and since this time, many different extruders have been developed to improve manufacturing performance in the food, metal, pharmaceutical, and composite sectors. In polymer-based production, extruders were initially used for the profile extrusion of pipes of polyvinyl chloride. Modular extruders, especially extruders for closely intermeshing counter-rotating twin-screw extrusion, have undergone intensive experimental study. The first detailed analyses of the extrusion process were related to classical flood-fed single-screw extrusion and concentrated on the melt conveying process, and, later, solid conveying. An early fundamental model for melting in a single-screw extruder was proposed by Maddock and Tadmore et al. Melting models and various comprehensive computer models were the basis for the development of flood-fed single-screw extruders. However, studies on starve-fed single-screw extrusion have only started very recently and mainly focus on mixing and melting capacity, with little attention given to modeling the process. On the other hand, twin-screw extruders are commonly used in modern industry. Such extruders can be divided based on the relative rotational direction of their screws into two types: co-rotating and counter-rotating twin-screw extruders. In a co-rotating twin-screw extruder, the maximum velocity is found at the screw tips, whereas in counter-rotating twin-screw extruders, the maximum velocity is obtained in the intermeshing region. It can be argued that the co-rotating mechanism provides better mixing as the material is transferred between the lobes. However, the counter-rotating mechanism generates greater pressure buildup, making it more efficient for profile extrusion. Many studies have experimented with different types of extruders in an effort to understand the material flow in the screws. Single and twin-screw extruders were compared as part of a design research focused on a simplified extruder for less developed countries for extrusion cooking and to process local food materials. Single-screw extruders are simple to construct, but are more likely to become clogged with material than twin-screw extruders. The single-screw extruder is the most common type of extruder, and it offers relatively low investment cost. Twin-screw machines are used for higher output. In extrusion, the die is a critical factor in influencing both output rate and product quality. The easiest way to increase the throughput of an extruder is to increase the screw speed. This easy solution typically results in poor melt quality caused by exceeding the melting capacity of the screw design and degradation caused by high melt temperature. Use of a smaller diameter screw can offer several advantages to achieve a higher throughput at higher screw speed. One important advantage of a smaller diameter extruder is better heat transfer characteristics. A higher throughput at a higher screw speed can be achieved with the use of a smaller diameter extruder. This offers better heat transfer characteristics. The objective of an extrusion die is to distribute the polymer melt in the flow channel so that the material exits from the die with a uniform velocity and minimal pressure drop. Except for circular dies, it is extremely difficult to create a single flow channel geometry that can be used for a wide range of polymers and operating conditions. Through an extrusion die, the exit velocity distribution is a function of the shear rate, temperature, and the heat dissipation of the polymer melt. In both single and twin-screw extrusion, all dies require adequate and uniform heating, with no dead spaces in the flow channels to prevent hot or cold spots in the polymer flow that might alter the melt viscosity or lead to resin degradation. The extrusion die performance depends on the design of the manifold geometry and on the operating conditions adopted during extrusion. The design of the extrusion die is a complex task because the extrudate product dimensions depend on the die design and on the polymer properties and extrusion process parameters. The die design process can be improved by integrating computational simulation with empirical data and by improving the extrusion monitoring instrumentation. A better and more developed die design improves product quality and reduces time to design and optimize the extrusion process, and thus results in lower costs. In twin-screw extruders, since the flight of one screw engages with the channel of the other, blockages can be prevented, thereby enhancing the mixing of material in the channels of the screws. In single-screw extruders, the material is retained for much longer than in twin-screw extruders, a phenomenon associated with stagnant layers on the screw surface. A twin-screw extruder has about 3 times more material output than a single-screw extruder of a similar size and screw speed. Theoretically, the material flow process can be divided into 4 sections. A. Feeding of the extruder. B. Transport of mass. C. Flow through the die. And D. Exit from the die and subsequent downstream processing. During material processing, the mass is transformed mainly by the shear force, pressure, cooling rate, shaping, and residence time. Conventionally, the extrusion channel is divided into 3 parts: A. The feed zone, B. The transition zone, and C. The metering zone. The material processing time in the extruder is termed the residence distribution time. Residence time distribution is an important parameter for product quality. Scientists compared the residence time distribution in counter-rotation and co-rotation twin-screw extruders and found that a sharper residence time distribution was obtained when using the counter-rotating twin-screw extruder. Residence time distribution was also studied by injecting a pulse tracer containing radioactive magnesium oxide into polypropylene into a Paschetti twin-screw extruder. The reproducibility of the results of the decayed magnesium, Mn, and iron, Fe, was detected using a scintillation crystal. This was used to determine the exit age distribution. This work was followed by another experiment, in which a radioactive magnesium oxide was applied to a Krauss-Maffei model KMD90 machine that was used to extrude polyvinyl chloride. Scientists compared the residence time distribution in 4 types of continuous mixers and concluded that the intermeshing counter-rotating twin-screw extruders had a narrower residence time distribution than the modular co-rotating twin-screw extruders and kneaders. This finding agrees with the work of other authors, who found that the residence time distribution is narrower for intermeshing extruders than for single-screw extruders or co-rotating twin-screw extruders. Most commercial extruders provide a choice of screws or interchangeable sections that alter the configuration of the feed, transition, and metering zones. This kind of modular design makes it possible to modify the extrusion process to meet specific requirements, such as mixing. Starve-fed screws are mostly seen in twin-screw extruders. The throughput of the extruder is not a function of the screw speed at a steady state. Unlike melting in single-screw extruders, studies of melting in twin-screw extruders have only appeared recently in the literature. Various models have been developed to analyze the melting process in twin-screw extruders. Based on these melting models, several comprehensive computer models have been developed, mostly for co-rotating twin-screw extruders. Reinforcements in processing. The increasing cost of pure polymer materials has resulted in the need for less expensive reinforcement or filler materials that do not negatively affect the strength and wear resistance of the resulting polymer profile. One such filler material is wood in the form of both flour and fibers. In addition, the increasing cost of timber and timber frames in construction products means that there is a demand for alternative solid products. Accordingly, the use of plastic extrusion profiles as a substitute for wood products, indoor and wall applications, as well as window frames and molding, has increased in recent years. The use of cheaper polymers as a filler material, for example, in the production of polymer films, is a significant way of reducing raw material costs. Also, the interest in the use of recycled polymers has increased remarkably because of tightening legislation. The replacement of virgin polymers with recycled ones offers an opportunity to reduce raw material costs in those applications where the use of recycled polymers is allowed. Growing interest has been focused on the use of other natural materials, such as hemp and sisal, as reinforcements for thermoplastics. Cellulose or cellulose-based fibers require coupling agents to improve their adhesion with matrices. Maleic and hydride grafted polyolefins, isocyanates, and silanes are commonly used coupling agents that improve not only the adhesion but also the mechanical properties of a composite. Polymer composites reinforced with wood or other natural fiber materials have shown remarkable improvements in the physical properties of polymeric materials. Experiments have been done using new natural fibers, such as sunflower hull sanding dust, SHSD, which has been used as a composite with polypropylene. Although obtaining the optimal processing conditions for extrusion has been iterative, some observations can be made about the fiber behavior in the extruder screws. The addition of SHSD influenced the crystallization behavior of the composite. Additionally, the crystallization temperature of polypropylene increased, while the melting temperature remained constant. Crystallization of polymers affects, for example, thermal, mechanical, and chemical properties of the polymer. The moisture absorption of the wood is one difficulty presented by the addition of wood flour. The loss of moisture within the extrudate can slow the extrusion rate as a result of an increase in viscosity. Moreover, unlike pure polymers, the addition of heat to wood flour does not improve the flowability of the extrudate. Encapsulating the wood fibers with resin and palletizing them can be used to improve processability during extrusion, where these palletized pieces can be mixed with additional resin and other process agents. Though this process requires double extrusion, it provides better wetting and smoother skin in the final product. Incorporating the proper amount of reinforced fibers, 5 to 20 volume%, into thermoplastic resin significantly improves dimensional stability, tensile strength, modulus, electrical properties, and corrosion resistance. These properties are related to fiber concentration, length, diameter, and distribution. To increase composite strength, the average fiber length in a matrix should exceed the critical length as much as possible without interfering with processability. The extrusion conditions are directly related to the mechanical properties of the product. Process effects on fibers. Over the past decades, scientists have investigated the effect of fiber damage on the properties of composites during compounding and extrusion. Different process factors, such as screw geometry and speed, fiber dimensions, feed rate, barrel temperature, and polymer viscosity, affect fiber breakage in the screws. Some studies have tried to model the fiber damage in screws, but modeling was also found to be challenging. The reduction in fiber length is most severe during the first processing stage when the fiber bundles are being filamentized. There is a limitation to the fiber length in the composite extrusion process. To increase the composite strength, the average fiber length in a matrix should exceed the critical length as much as possible. Therefore, it is important to evaluate the effect of processing variables on the extent of fiber degradation during extrusion. Reductions in fiber length and distribution have a negative structural impact on the composite product. A shear stress concentration occurs near the fiber ends, which is where failure initiates. Greater fiber breakage leads to more fiber ends, which act as sites for stress concentration where the initiation and propagation of interfacial cracks occur, thereby leading to tensile stress failure. It is challenging to experiment with new materials and material combinations because there are limitations on the extruder's conditions, especially when working with fibers, making numerical analysis very difficult. The pressure in a twin-screw extruder can be controlled with reverse conveying, i.e., a pressure release, and forward conveying, i.e., a pressure increase in the screw sections. Generally, the pumping capacity of the screws decreases if the fluid being pumped is non-Newtonian and increases as the fluid becomes more Newtonian. The slip at the screw and at the die has an important impact on the flow rate and extrusion pressure. It was found that increased slip at the screw decreases both the flow rate and pressure, while increased slip at the die increases the flow rate and decreases the pressure. Fiber degradation under low shear deformation is negligible, as presented in the study based on a comparison of the fiber length distribution before and after extrusion. Extrusion with fibers is efficient when using multiple extrusions and palletizing. The apparent viscosity at a constant shear rate as a function of the number of extrusions decreases gradually as extrusions are repeated because of the degradation of the matrix polymer and a reduction of the fiber length. An increase in the number of extrusion cycles decreases the length of the fibers. During the first extrusion, severe damage to the fibers was already observed regardless of the extrusion, polymer's speed, and shear rate used. Extrusion is an energy-intensive process. Therefore, the optimization of process energy usage while maintaining polymer melt stability is essential to produce high product quality at low unit cost. Thermal stability and energy efficiency are strongly influenced by process conditions, the polymer material and extruder used, as well as the process control and monitoring system. The process engineering and modeling play a key role in improving the energy efficiency of the extrusion process. Screw assemblies and extruder dies are two major design areas that have a significant impact on the degradation of particles and the mixing of materials. A modifiable design could be created to analyze screw efficiency, and the design could be computationally optimized before proceeding to manufacturing in an extruder machine. There are many different software platforms, such as SolidWorks and NSYS, available on the market that include packages to design machines as well as to analyze or simulate processes. This allows easier data transfer between different packages, which shortens design time and improves productivity.